Okay, so we're going to extend our talk of essentially projectile motion, everything, and motion in general. We're going to talk about relative motion. This is really important for like aerospace engineering, where you have multiple reference frames that could be happening, because you could have a reference frame or at least some observers on the ground watching what an aircraft is doing, and then you could also have the people in the aircraft, and they have their own frame of reference, and they're also seeing events happening, and watching their airspeed versus ground speed. So you could have situations where there are multiple frames of reference, and we need to make sure we know how that we can get these frames of reference to essentially talk to each other, and make sure that any event that happens, no matter how it's measured, we can actually relate these different frames of reference, and make sure we have consistency as we talk about these measured events. So let's think about just a really simple example here. Let's consider the motion in two different reference frames. Suppose a sports car and a minivan pass a pedestrian standing on a sidewalk. Okay, so you can see our pedestrian down here and our minivan and our sports car. So the sports car is maintaining a constant speed of 55 miles per hour. Okay, and then the minivan is trying to keep up. However, the minivan is not as fast, and can only maintain a speed of 54 miles per hour. So you can see that there's a difference. So there's a difference in velocity of 1 mile per hour. There we go. Okay. So what the pedestrian sees is essentially the cars travel away at 55 miles per hour and 54 miles per hour respectively. Okay, because the pedestrian, remember, their velocity is 0 meters per second. They're not moving. So any motion that happens, they're going to see the true value of the speed of these cars. But the driver of the minivan, they see something very different. And I'm sure, if you drive a lot, you've noticed this before. When cars pass you, or when cars are going faster than you, it looks like they're just barely moving away slowly from the reference point of your car. Okay, so the driver in here, I'm going to draw a little frame of reference. So given what the driver sees this change here. The driver sees this change that's driven by that 1 mile per hour difference. Whereas the pedestrian over here, this person is seeing the actual absolute values of the speed. So it really just depends on where the reference frame is, because we've got this red reference frame here in the car, but we also have we also have this other stationary reference frame according to the pedestrian on the street. Okay, so let's formalize this just a little bit. Okay, so we still have our sports car moving away at 55 miles per hour, and we still have these two reference frames. So the pedestrian's reference frame, we'll call it S, capital S. Capitals are important right now. It's stationary, it's not moving. Okay, so here's our pedestrian from the previous slide. Okay, now the minivan's reference frame, we're going to call it S prime, and it's moving along with the driver. Okay, so this coordinate system, this X and Y axis, it's going to ride along, it's stuck to the car. Now in the pedestrian's reference frame, the location of the sports car, okay, remember we're just looking at the sports car up front right now. Okay, the location of the sports car is just identified by R. So it's just the position of the sports car. That's easy. We've been doing this for several weeks. You guys know how this works. That's no big deal. But we can also write R as a combination of big R and R prime. Now the question is, what is big R and R prime? Before I explain that, I do want to point out that this R, our R, the R that's graphed right now from the pedestrian to the sports car, this is just going to be broken down into two separate vectors. Okay, and we're going to talk about two separate vectors. Big R represents the position of the traveling reference frame. Okay, so big R is going to point to the origin of this traveling reference frame with respect to the pedestrian. Okay, so here we see this R. Oops. There we go. Let me get back to where we were. Okay, perfect. So we see this R here is right there with the origin. Okay, points from the origin. However, a big R here just points to the origin of S prime. Okay, so the big capital letters like S and R, they are just pointing and they're pointing from one origin to the other, and that is all. That's how we're characterizing how these two reference frames are moving with respect to each other. That's what the capital letters are for. Okay, but don't forget we also have this R prime. So little r prime star in the traveling frame of reference. Okay, so we've got this S hat frame of reference here, or this S hat reference frame. So we have this S hat. I'll draw it in green. So all the hat stuff is going to be within this frame of reference. All the not hat stuff is going to be in the pedestrian's frame of reference. Okay, so here's our R hat, or sorry, the R prime, not hats. There we go. Yes, let me say that one more time. The R prime stuff and all the prime things. So prime is the traveling reference frame. The non-prime values is the stationary. So that's why we have this S prime traveling with the car, and then we have the R prime distance as measured by the car. So we can even include this in green. So essentially the idea is how can we represent the green stuff, the traveling reference frame, by the red stuff in the stationary reference frame. All right, so let's formalize this definition of reference frame real quick. So essentially a reference frame is just a coordinate system where an experimenter makes position and time measurements of just whatever's going on. Who knows? It could be anything. But basically, it's just how you're setting up your grid, and that is a reference frame. Now, we could have two different reference frames, just like we saw the pedestrian have a stationary reference frame, and then the driver of the minivan could also have a reference frame. Okay, now two reference frames could be moving relative to each other, and that velocity is just capital V, and that's just the change between the two with respect to time. The change between the two distances. Okay, so notice we have capital V and R are associated with S prime. So do remember that the capital letters are associated with just your X and Y coordinates in the traveling frame and how they're moving. Okay. Now for our work, we need to assume that the frames are oriented the same way. So essentially, They're turned the same way, they're pointed the same way. It's going to make our lives a little easier. And then when we start our stopwatches, when we time an event, essentially our stopwatches need to be synced up across the two. They can be moving, but we want to make sure that whatever event we're measuring at, they happen at the same time for both. Okay, so same t for both. Now this is just like the projectile motion problems where we had the same time in the x direction and the y direction. Here we're going to have the same time for both reference frames. Now this is very important right here. We're also going to assume that velocity is constant. Okay, so even if one of these reference frames is moving, we're going to assume that it's not speeding up or slowing down. Now this constant speed setup, that's called an inertial reference frame. And as soon as you move to a non-inertial reference frame, so when you have a situation of speeding up, slowing down, that gets really complicated. That becomes like one of Einstein's relativity problems, and it's gross. So we're only right now looking at these simplified examples of just inertial reference frames where the velocity is constant. Oh, good grief, I can't change my slide. There we go. Okay, so a simple example would be if two different groups observe a flash of light and measure its position in their respective reference frames. Okay, so we have group S. Now I will mark group S in green. Okay, so we have group S, and they measure some position of this flash of light with coordinates X and Y. Okay, so this is stuff we've done a million times. We just have an X coordinate and a Y coordinate. Okay, but now group S, they're here in this reference frame. Okay, so they have a Y direction, X direction. Now they measure this flash of light over here with some X and Y coordinate. Okay, well, so group S prime, okay, I'll do that here in orange. So group S prime, they measure the exact same flash, but they're standing somewhere else and they're using a different origin. Okay, so this is what group S prime measures. So this is going to be an X prime, Y prime. So we have the same event measured from two different reference frames. Now, again, remember, we can rewrite R. Okay, and this is how we're going to build this relationship. Okay, so the relationship between these two, actually, let me use a different color to make some notes here. Okay, there we go. So we're going to take S and S prime, and we're going to relate them by R. So you'll notice this R, can even switch back to the original color. This R, okay, our long green vector here that was measured by group S. This can be broken down into, let's see, my blue vector over here in the picture. So where that other reference frame is, so the relationship between group 1 to group 2, that's represented by R, plus this piece here, plus how group 2 measured the flash. And if you look, you can actually see this. I'm going to do this in black, but this addition, you can see just from doing vector addition that it's just big R plus little r prime. So essentially, where the reference frame is. And that's going to be plus the measurement in the frame. Okay, so if we're over here, if we're part of group 1, we can just use those two things and reconstruct the position of the flash. So let's continue this example. We could ask the question, what if S prime is moving? Okay, so maybe group 1, S, they were standing by the road, they measure a flash, and then group 2 is driving by and they measure the flash in the same way. It's just their reference frame is now attached to a car and they're moving. So remember that this flash happens in one instance of time. So whatever coordinates we write down, whether it is, let me write it over here, whether it is xy or x prime y prime, these happen at just one particular instant in time. So whatever value they measure is just going to stay the same. So in that situation, we can actually take our original relation here. Okay, so we can take this relation of the position of the event and actually adjust this for a moving reference frame. Okay, so where the flash happened with respect to S, okay, so this is going to be big S. Now we know that R is not going to change, because if we measure this thing at XY, well, our position is stationary, our reference frame is stationary, that's not going to move. Okay, now when group 2, so when the S prime people, when they measure this flash, they measure it at X prime Y prime. Now that's not going to change for them. They said, okay, at this one time, okay, so this is at some t, so I'll just call it at t1. So at some time, and this is true up here, at some time we measured this event at X prime Y prime. Now these numbers are not going to change. However, where their coordinate system is, this will change over time. So the idea is that we have these x prime, y prime coordinates, but the origin keeps moving. Okay, so here's what needs to happen. We have, and I'm going to see if I can do some more colors here. So we have this position here, r prime. Okay, we measured this event with x prime, y prime. This is their coordinates here, x prime, y prime. Those numbers are not going to change. R prime, it's set. However, our origin, our reference frame, it's moving. Okay, so we need to shift that reference frame to make up for the motion that is undergoing, essentially. Okay, so this is from the shifting. And this is called a Galilean transformation of position. So if we know where and when an event occurred in one reference frame, we can use this relationship here to transform it into another reference frame. Okay, so we can transform the position into any other reference frame as long as it's inertial. So I'll leave a note, inertial only. We can also do the same thing with speed. So we can actually do a Galilean transformation of velocity. And all we're thinking about here is just the rate of change of an object's position. This is possessive, there we go. The rate of change of an object's position is of course given by dr over dt. We've seen that so many times before. So let's actually start with our position r. We know we can break it down into two pieces. So let's think about this and take this derivative. Okay, so we know the velocity is dr dt. But then we can distribute this derivative and take the derivative of r prime, and then take the derivative of big R. Okay, we can just write that here. Well, that's just dr prime dt. Now we have this really basic equation from the previous slide, essentially where the position of r is given by the velocity times time. Okay, well, we can take the derivative of that, and we're left with big V. And of course, dr prime dt is just the velocity in the prime direction. So it turns out that the velocity of an object as seen from a stationary frame or some primary frame, we could call it our frame, is just the speed as seen in a different frame plus the velocity of that different frame itself. Okay, now it's important to remember that the lowercase letters v, v prime, those are velocities of objects, and then the big velocity is the velocity of the reference frame itself. So let's look at some quick examples. All right, so Cleveland is 300 miles east of Chicago. A plane leaves Chicago flying due east at 500 miles per hour. Okay, well, we got that here in our picture at the bottom. We've got Chicago labeled, we've got Cleveland labeled. The problem is the pilot forgot to check the weather and doesn't know that the wind is blowing to the south at 50 miles per hour. That's a lot of wind. What is the plane's ground speed? Okay, and then where's the plane 0.6 hours later when the pilot expects to land in Cleveland? Okay, so first step, we always model. So it looks like we're going to let the Earth be reference frame S. Okay, and then Chicago, Cleveland are at rest in Earth's reference frame. That totally makes sense. So the air is going to be S prime. Okay, so we have this moving reference frame. So I'm going to make a note up here. S prime moves with the wind. Okay, looks like everything else is essentially just saying that our reference frames are going to point the same way. Now, first question is, let's see. Yeah, what is the plane's ground speed? So that's just the velocity relative to the ground. This is where it gets a little tricky, so we need to be careful. All right, so we have the prime velocity. Okay, so this is what the wind is seeing. Okay, now this is v prime. So what you have to remember, and this is important, over time our origin moves with the wind, right? So our origin starts here, both origins, the origin in the wind and the origin on the ground. So after some time, our origin moves down here. But see, since the wind is also blowing at our origin point, it looks like the plane is still just moving to the right of the wind origin. Okay, so this is S prime. Okay, and then after a little more time, our origin gets blown further down. So what's going on, since our origin travels with the wind, is if we're sitting on that origin point, it just looks like the plane is moving directly away from us. There's no angle involved. So that's where this 500 miles per hour comes from. To us, if we're a leaf in the wind, blown south from Chicago, if we're riding on that leaf, it just looks like the plane is moving at 500 miles per hour away from us. Okay, well, there's no movement that we can see if we ride with the wind. There's no movement in the y direction. So this piece here is just going to be our relative velocity in this wind frame, and it's just got the plane flying away from us at 500 miles per hour. Now, this is where we take into account this big V. This is where we actually take into account the speed of this new origin. So if you look back here at the picture, that's going to be here. Okay, so green's going to be this speed as our different our relative origin in the wind is going to be moving down or being blown to the south. That's taken care of right here. So we have no wind in the east-west direction. It's all in the south. So wind to the south. And that's just the negative 50 miles per hour in the j-hat direction. Now all we have to do is just combine our x direction, our y direction. You guys have done that before. And we're left with this nice, just one vector. This is the ground speed. So say relative to Chicago. Okay, we could also say relative to Cleveland, but this is essentially if someone in the control tower at the airport is watching the plane, this is what they're going to see. Which makes sense. If you look at the picture, what we have here that we just come up with is this vector, the actual what people on the ground are seeing the plane do. Now we can actually calculate the speed and not just the velocity of this, and that's just adding the components in quadrature. So we're going to add the 500 squared plus the 50 squared, okay, and that's going to take this velocity and turn it into a speed for us. And what's really interesting is the people on the ground would say like, oh, this plane is traveling at 502 miles per hour. But if you remember from the problem, the plane thinks it's flying at 500 miles per hour exactly. So what's going on is getting a little bit of a boost from this wind. Because remember, if the total or the max speed of the plane is 500 miles per hour, all of that is going into the left-right direction. It's all going into the east direction. There's no extra velocity to actually move the plane down. That extra velocity comes from the wind to move it to the south. So because we have this, all of the because we have all the velocity from the plane, we have to add the extra wind velocity, and that addition makes the plane look like it has a slightly faster speed than it really does, if that makes any sense. We're just getting that speed boost, and the overall total speed looks a little higher because of it. Now, what about its location after 0.6 hours? So we can actually just look at its x position and its y position. Okay, and this is pretty easy. So we just take the velocity in the x direction. Okay, well, we know its velocity in the x direction was 500 miles per hour. There's no wind in the x direction either. Wind. Okay, so there's nothing to change this. This plane is always going to be flying to the east or to the right with 500 miles per hour or speed. The wind is only in the vertical, so there's no extra effects there. So we have this velocity Vx times the amount of time we're talking about, which is just the 0.06 hours. And it turns out, yeah, we're going to get in the x direction, at least to the east, we're going to get that 300 miles that we needed to get to Cleveland from Chicago. But look at what happens in the y direction. So here we do have wind in the y direction. Okay, so over time, this negative 50 miles per hour wind over this 0.6 hours is actually going to shift us 30 miles south from where we want to be. So the plane, what you might see is from Chicago to Cleveland. Over time, you're going to see this with a change in distance, negative 30 miles. And that's just coming from the wind from the north. So what we can do here is actually, if we look at this triangle here, we want to know what heading the plane was flying. We can just take our big piece here, so our velocity of the reference frame, which I've got here in orange, and then the actual what was going on the ground here. Okay, we can use these two vectors with a tangent function here. And it turns out that the plane was actually flying about 6 degrees south of east. Okay, so this was about 6 degrees off. I'll say roughly 6 degrees off. Okay, well, let's think about how we can correct this. Okay, so a wiser pilot was flying the same route on the same day, but she remembers to take the a wind into account. Okay, now if she wants to correct her if she wants to correct her path, it gets a little tricky to think about. So the question is, how does she have to fly her plane to correct for the wind, and then how long does it take to reach Cleveland? Okay, so we can model this just like in the last problem. The idea here is that we need to turn the plane a little bit. Okay, so we're going to rotate the plane a little bit, fly into the wind, and that's going to cancel out the effect of the wind. All right, so what is required? Essentially, what do we want the people on the ground to see? Okay, so remember that this is the ground, so this is big S. Okay, when people are watching from the control tower, we want them to see the plane flying directly to the airport, okay? So we want a direct path to Cleveland as seen by Chicago, Cleveland. Okay, well, essentially, that means we want our X piece here, so our horizontal velocity, remember this is still all the stationary frame on the ground, so we want our X velocity of that. Well, we just want it to be straight across our 500 miles per hour, but remember we're flying at an angle. So we just want the X component of our 500 miles per hour. Okay, that's going to give us right here, it's going to give us the velocity we're going to use to get to Cleveland in the X direction. Now, here's where it gets a little tricky. This is what you got to remember. We want to cancel out the velocity in the Y direction. Okay, so we've got our Y component of the velocity. We have a little piece of the velocity going up now. You can see here, I'm going to change my color to green. Okay, so you can see here, okay, we have some velocity going up because the plane is also angled up. That's where that comes from. We now have a Y component. Okay, well, that's going to be just the Y component of that 500 miles per hour. But, so this is going to be the plus J hat direction. Okay, we're flying up. We want to cancel out the wind from the negative J hat direction. Okay, so we have our north component of our velocity. Okay, we're sort of flying up, so to speak. And then we also have the wind coming down. So those things need to cancel out. Okay, so that's why I set the difference equal to 0. Okay, so whatever angle we need to fly at, okay, we have to select our angle to make this equation equal 0. Now, if you do some algebra, all you have to do is just take this equation and solve for theta. So it turns out if we fly at an angle of 0.74 north, okay, so toward north, okay, that angle of 5.74 degrees is going to cancel out the wind, okay? That cancels out the wind, and you can see that up here in this original equation. I'm running out of space, but you can see that here in this original equation. Essentially, if you plug in the 5.74 degrees into sine theta, that's going to make sure that the stuff on the left-hand side equals 0. Okay, so if we fly at a heading of 5.74 degrees, it will look like from Cleveland and Chicago's vantage point, it will look like we're flying straight across. We're not going to be affected by the wind. Now, the other question is, how long does it take to get there? Well, we know it's 300 miles in Chicago and Cleveland's reference frame. They're on the ground, it's stationary. So the distance between these two places is going to be 300 miles. That's not going to change. Now, since we're flying straight across in the essentially the x direction, we can just take our x component of velocity, right? And of course, this just comes from velocity equals distance over time, and we're just going to solve for t. Okay, so we know our x piece, we know our distance, we can plug that in, and it turns out it's going to take just a little bit longer. So you'll notice we have this extra like 0.004 hours, which is just a few extra minutes. And that's because we're having to fight the wind. We have to take some of our velocity and put it into the y direction, or the j hat direction, to cancel out the wind. Therefore, our x speed is going to be a little bit slower. Okay, so that's pretty much everything as far as relative velocity, or just relative motion in general. Uh, do keep in mind that these are kind of tricky to think about, because you always, when you do these problems, you have to think about, okay, where's this extra velocity coming from? Why is it there? And how can I cancel it out? So just like here in this line, you need to be thinking about how to get rid of these unwanted velocities. You need to be thinking about what you want the people in stationary frames to see, so to speak. Just like here, we wanted the people in Chicago and we wanted the people in Cleveland, if they were watching us fly, we wanted to make sure they saw us travel in a straight line. Okay, it's tricky to think about, but that actually helps you set up these equations. You know that in the big S frame of reference, something's got to equal 0. In our case, Vy had to equal 0. So here's where pictures get really important. And going slow and taking your time is also very helpful. So as always, as you work on these, let me know if you have any questions. I'll be more than happy to help.